Hello and a very good morning, everyone. My name is Nur Aina Zira binti Muhammad Yunus. I'm a student from University Technology Malaysia, UTM, and currently I'm serving as intern students in UKM, University Kebangsaan Malaysia in Bangi. So now I will make a short clip about how to use Mathematica BVPh 2.0 for the first time if you are the beginner. So I'm going to use an example from this journal article, which is Ham-based Mathematica package BVPh 2.0 for nonlinear boundary value problems. So the example that I'm going to use is illustrative example. Sorry. From this example, 9.3 illustrative example, and this system models two-dimensional flow of an upper convected Maxwell fluid in a rotating frame, and it has been solved by Sajid by using the hand. So first thing first, I'll show you step by step on how to open it for the first time. So I save my Mathematica apps in this folder. So you just click the folder, you just click the apps. Okay, so if you are new, you just want to code for the first time, you can just click this new document. But as for me, since I've done the codes, so I'll just click to the files that I wanted to open. So I'll just click this run illustrative iron, and then iron because it's my name. So you can just put any names you want actually. So to open a new one, to open another folder, just click File, Open, and then I'll click this Illustrative Iron. So there are two files that you might need. So the first one is the one with this extension .m, and the second one is the another one with extension .nb. So first thing first, I will talk about this 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 file. Okay, so this code that I made is based on the illustrative example that I showed just now, which is this one. So 9.1 and 9.2 are the governing equations, and 9.3 and 9.4 is the boundary conditions. So mm so yeah, this is the first thing first before you started to insert your equations. So you have to write this type eq is equal to 1, which indicates that this ODE system has no additional unknown variable. And the another one is number eq is equal to 2 because we have two equations that we are gonna solve in this case. So next, this line and this line indicates this line, the first equation, and F2 and this line indicates the second equation, 9.2. So I made a very specific explanations on this. You can pause and read. Yeah, you can pause and read. So 1, 2, 3, 4, 5, 6. These 6 lines are the lines that you need to write to code your governing equations. So the next one is boundary conditions. So there are 5 boundary conditions right here. Let me show you from the first one. Okay, this one, 2, 3, 4, and 5. So you can just include it here. You got 1, 2, 3, 4, and 5 boundary conditions. So next is the one solution interval and also integral interval for the squared residual area. So there are 6 interval that you need. Since we have two equations, so we need four of these four solution interval, which is from 0 to infinity and also from 0 to infinity for equation 2. And then integral means right endpoint of integral interval 1. So if the value of ZR integral 1 is finite number, then you have to put that number. Let's say the number is 3, then you have to put 3. But in this case, since the right interval is infinity, so it has to be set to a finite value, and the value that we choose in this case is 10. So I put 10. So the same goes to this one. And then for auxiliary linear operators, it's also given in this PDF here. These two. Okay, sorry, this one. Okay, these two. So you can just put inside here like this, and then initial guesses and also physical parameters. They the physical parameters differs depends on the equations or problems that you're gonna solve. So some of problems might have a lot of physical parameters, but in this example, we only have two physical parameters, which is beta and also lambda. And then lastly, you have okay get optimal CNOT. CNOT is the optimized convergence control parameter. So you can see here 3 means that ordered approximation is used, empty list, C naught, C naught 1, C naught 2, and alpha. And then to get the 10 order approximation, you can just use BVPh 1 until 10, or if you want 30 or 20 order approximation, so you just change this part to 20 or 30 or any other numbers you want. And then you can just click shift enter, and then you can run everything. And then for the next file, which is uh, the notebook file, so first of all you have to clear all global variables using this command, and then read in the package BVPh 2.0. So for my directory is D data D, and then Wolfram Mathematica 13.2. So that's why mine is just this one D, and Wolfram Mathematica 13.2 BPH 2.0. And then you have to set the current working directory like this, and then just read the data putting in the name of this file, which is illustrative m. So for this one, you can have this, and then you can just click shift and enter, and you will succeed. You will see that this package BVPh 2.0 was successfully loaded. And then if you want to plot the graph, so for this one, so it was like this, and then you can just if you want to plot the 10 approximation, you can just do it like this, and then you will get this graph. For this equation, this is the graph, and if I want to plot another graph, which is to plot the curve of the total error versus the order of approximation, then I got this graph. This is total error and order of approximation. Finally, this is the output that I get. So you can see the values of control parameters in BVPh, and then these governing equations, the boundary of conditions, we got five boundary conditions, and then the domain, which is the solution interval, integral interval, and then convergence control parameter, which is initial guesses, auxiliary linear operators, auxiliary functions, convergence control parameter, and then computing optimal values, which is the C node. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, because we just approximate for 10 order Ham approximation. Okay, that's all. Thank you.